So I will talk about the HYDRUS-1D MODFLOW module, and my colleagues has implemented it for a catchment model, and as far as we know, it's one of the first applications of this module to a real catchment. And we had some problems and difficulties for implementation, so we learned some lessons. The work was mainly done, or was solely done by my two colleagues, Leterme and Gedeon. So I will give a short introduction, and then we'll discuss shortly the different steps in the implementation of that model, so how we define different zones, which difficulties we had, and we will compare it with some experimental data, and from that it will be clear that we still have some work to be done. The catchment we are working on is the so-called Nete catchment in the northern part of Belgium. And in our institute we are interested in this catchment because it is located above the hypothetical or the reference site for the deep disposal of high-level radioactive waste. So we invest a lot of time in this catchment. And for the time being, the groundwater flow model was developed in MODFLOW, and the surface has 9,644 active cells, and each cell has an area of 400 by 400 meters, and the spatial or the vertical discretization is within 16 layers. We have some different material types like disc sands, castellate clays, Pliocene sands, and so on. And so the bottom of the model is by the boom clay, so that's the aquitard where the disposal site might be installed within a few decades. And you see that it's quite complex in geometry because at one side it's very thin, that's where the boom clay is at the surface, and then it's going deep up to 200 meters at the other side. Up to now we use a steady state groundwater flow model, and we had as an upper boundary condition a uniform constant recharge of 208 millimeters per year. This value was obtained by a methodology very similar to one of the presentations yesterday, where we use HYDRUS-1D for only one soil type and one vegetation type. Of course, we want now to bring more realism inside this groundwater flow model, and so the goal of using this HYDRUS MODFLOW module is to have a more realistic estimate of the spatial and the temporal variation in the recharge from the unsaturated zone to the saturated zone. The way this is done in this module is so you group the active cells in the MODFLOW in zones with similar hydrological behavior. And for each of these units, you have one HYDRUS-1D model. Okay? And so after MODFLOW, within a time step or within predefined time steps, when MODFLOW has done his simulation, you calculate the average groundwater table for all these active cells within one zone, and this is given as a boundary condition to HYDRUS, which is representative for that zone. Then you do the water redistribution within the HYDRUS, within the unsaturated zone, and you get recharge and or discharge fluxes, which are then assigned to all the active cells for that zone. So that's the way this module is working, and which we tried to implement for a catchment. So we need to have we need to define the number of zones. So in principle we can have 9,600 zones for each active cell, one zone, but that will be computational too intensive. So you have to follow some guidelines to define your zones. And we did it, well, at the start of the simulation, of the exercise, we defined 3 different criteria. The first criteria was the groundwater depth that we obtained from the calibrated steady-state groundwater flow model. The second criteria was the soil type, and the third criteria was the land use. But in this exploratory phase of the study, we decided to use only one soil type, which is basically in pot soil, sandy soil in that region, and one land use cover. We assumed that it was grass over the whole catchment. So that's a strong simplification, but that was more as an exploratory. We are still in an exploratory phase. Then some practical issues. So this was first a simulation with only 6 zones. We defined only 6 different zones. And in this figure here, you see as a function of time, the daily values for discharge. This is a purple line together with the evapotranspiration rate. And you get on the other axis the recharge to the groundwater together with the precipitation. And you see you need a warming up period of the model, because during the first 180 days we just get oscillations of recharge and discharge not following any expected thing or reasonable thing. But about 180 days the recharge and the discharge start to stabilize and also follow what you expect from rainfall and dry conditions. So recharge during dry periods and recharge during wet periods. So for this example here, it was reached within 60 days, 180 days. So this is more or less the same, but this is with the predicted average groundwater depth with MODFLOW. So you see also for some zones there is very strong oscillations obtained, but then after a while we get stabilization of these groundwater tables. This is another example for the simulation with 10 different zones. So here we have simulation up to 2000 days more or less. The color scale gives you the water content as a function of depth, and the red dots are the water fluxes to the groundwater or the recharge and discharge. So if it's positive, it's up to the unsaturated zone, and if it's negative, it's down to the water. This is for zone 2, which is a shallow groundwater table, and basically quite fast you see that we get stabilization of the groundwater table, and we have only the seasonal variations in the groundwater table, and you also see that in the fluxes. So for a zone with a shallow groundwater table, you can obtain the stabilization quite fast. This is then the example for a deep groundwater, a zone with a deep groundwater table. So here you see that for about 1000 years we get a discharge, which is not really expected for such a deep groundwater table. It also does not follow the seasonal variations, but then after 3 to 4 years it starts to also follow the fluxes, starts also to follow seasonal variations, and it's always recharged a little bit what you expected from a deep groundwater table. So this module requires several years to warm up, let's call it like that. Then we have also some issues about oscillatory behavior, which could lead to chaotic behavior or non-convergence. So we should, so you see here, this is oscillator behavior in the discharge. So we need also very small or relatively small time steps in the MODFLOW to minimize these oscillations. So we were then able to have no oscillation anymore in the discharge, but as you can see, we still have oscillations in the recharge. But this is possibly also linked with the next problem we have, namely certainly for the shallow groundwater zones, we had MODFLOW predicted groundwater tables above the soil surface, and it was not a few, but it was relatively a large amount, certainly for the zone where there's only, where the average groundwater table was at 1 meter. So the blue colors indicate the number of cells where during one time in the simulation we have seepage, so it's called a groundwater table above the surface, And this is certainly not the case in that catchment. It's not realistic. So it's and at that stage here we just remove this water from the surface, not by just remove it. So we do not use any runoff model to capture that water. So this might induce also this oscillator behavior for that zone. The reasons are probably, but we have to further explore that the zone is zone 1. We should use more specific, well, more diversification in the definition of that zone. And secondly, we didn't change the values of the hydraulic conductivities of the layers of the groundwater. And these were strongly biased on the steady-state model assumption of in the model. So these values might not be representative for a case where we have variable recharges. Okay. That's then the final result I want to show you. So we have we divided the catchment in 20 zones only based on the groundwater depth from the steady-state model, and we didn't change the values, the hydraulic conductivity values of the groundwater model. So this is the distribution of the different zones, and you see the shallow groundwater zones are quite present here. That's probably why they have such a large impact. We did a 10 years warm-up and a 10-year simulation. And here I show you for every zone the average groundwater recharge. And also, as we have seen yesterday in the presentation, if you go deeper, if your groundwater is deeper, the recharge is less sensitive to the groundwater depth. So that might be a way to optimize the number of zones, have less zones with deeper groundwater tables, maybe discriminate them with land use and soil vegetation, and put more effort in the zones with the shallow groundwater table. We can also compare the groundwater levels, because we have a piezometric network in that catchment. So these are the locations of the measurements. So here you see for zone 1, so that's the shallow groundwater table, measured groundwater depths during almost 30 years, and our simulations. And so here you see we are way off the measurements for the reasons I already mentioned. Probably the zone 1 is too generic, probably, and combined with this problem of seepage and the not optimized parameters of the groundwater model. But for zone 2, the correspondence is not too bad, and also for zone 3, the comparison between the simulation and the observation is not too bad. So the red line is basically the average groundwater depth for that zone, and the pink area, that's the variability of the groundwater depth within that zone when obtained from multiple. Okay, so as a summary, well, the summary is more what the perspectives, the further challenges. As already mentioned a few times, we should invest some more time in probably defining more realistic zones by including some information about land covers. Also some topographic information can be handy for the shallow groundwater depth. And well, we need also to include more precision, solving the problem of the seepage of the shallow groundwater tables. But a key issue here is also the computational time we needed about, on the standard computed, 4 hours of simulations for these 10 years. That means that, and for 20 zones, so that means that we cannot extend it to 2,000 zones and doing full calibration and things like that. So the timing is also very sensitive to the number of zones. But we think we can also, with this, with the variability of the groundwater depth within one zone, that can give us a guideline how to maybe distribute the different zones. And we can also do some calibration versus the piezometric data. So that's my talk.
Okay. Okay, exactly on time. Yes, please.
Yes, in which kind of was the coupling by the both programs? Was the coupling by the program? You have changed the codes, the program codes, or you have coupled the both program by the data files, by the boundary conditions?
I didn't. We just choose how it.
It's directly linked. So
Okay.
it's the both codes run are coupled fully and they run simultaneously. And so and MODFLOW sends information about position of groundwater level at the end of the stress periods, the HYDRUS, and HYDRUS then averages the recharge. So it's run simultaneously. So it's not through the files.
And we have also coupled our model is also a Groundwater model.
Okay.
Yes, please.
Sorry, just one question, if I understand. So what do you think, what's the reason why do you have such a long warm-up period? It's longer when the ground table was lower.
Yes.
I understand. So the problem with the unsaturated zone?
It has, I haven't think about it very much, but it's linked with the groundwater depth. That was clear. So it needs just longer time for stabilization. Yeah,
because it's quite long in some periods.
Well, it was 3 to 4 years.
Yeah.
So
Well, we first have to overcome these very strong oscillations, and then, well, when the first zones, the upper zones, become stabilized, then I guess it's also a kind of sequence of stabilization.
So how do you define initial conditions?
Oh, I don't know. Probably they started from the steady state equilibrium. Yeah. So they use the average, the steady state groundwater flow model that use that initial condition.
So do you have different numbers of elements on different verticals?
What?
Do you have different number of elements on different verticals if you have such a huge differences in beta zone?
Different?
Well, you have groundwater level has different depths, right? At different parts of the domain.
Yeah.
So do you have different, and then you have these HYDRUS verticals.
Yeah, so you have
Do you have different number of nodes?
so every active cell has its own groundwater table, but at the beginning they are quite different.
okay, thank you, Leterme. And last presentation of this session was changed, but we have Christina with us to give us the last presentation.